Next problem in the backtracking category is called word search. We are given an m times n grid of characters called word and a string word, and we have to return true if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So in the first example, we have A, B, C, C, E, D. So in this case, we are starting with letter A, and then we can either go, for each of the cells, we can go down, we can go left, we can go up, and we can go right. Considering also that we have to be inside the boundaries of the grid, and that we are not, and also consider that we are not visiting the same character more than once, which basically would meant that we are using it more than once. So in this case, we can go right, and the next letter is B, which corresponds to the second letter, so we are good. We can go again right, which is our letter C, that's our third letter, so we are good. Next, if you go right, we will basically get to the E, which doesn't really match our next element, which is again C. So we have to backtrack. We have to go back and remove this letter from the letters that we have chosen, and we go basically to another direction. And let's say in this case we can go down, and the next letter matches the fourth letter C in our word, so we can continue our process. Next, we could go to the S. We could see that it doesn't match the next letter, which is E. And then when we would go basically down, the E letter matches the E letter inside the word. And next, we can go to the right. We would see that it doesn't match the last letter in the word, which is D. So we cannot go down. We have already been up. So the only direction that we can go is left, and the letter D matches our last letter. So the next time when we go, we will basically, when I say we are moving, we are just calling our helper function recursively and propagating the direction to the next helper call. And in this cell, when we move to the next cell, when we call the helper function again, we will have a base case, and our base case will basically be, okay, you are currently you have already found all the letters inside the word, so you can just return true, which we will do. In the next case, we have the word SEE. So the first thing is always to find the first good position for our word. A is not a good position because it doesn't match the first letter S. This S is it might be a good position, but we will soon see in the when calling the helper function cursively that we cannot find anywhere in the neighboring cells the next letter, which is E. But if we choose this S and then move down and move to the left, we will find the word C. As we can see here, we have A, B, C, but B is nowhere to be found because the letter B is not even present inside the grid. So we cannot form the word A, B, C, B, so we return false. Now M is the number of the rows, while N is the length, the number of columns. Their size is ranging from 1 to 6. The length of the word is 1 to 15. And the board and word consist only of lowercase and uppercase English letters. So to find the first position that's a good candidate because it matches the first letter in the word, we will basically traverse through all our each row and each column, basically our grid. So we will have two nested for loops that are traversing through the matrix, through the grid. For each, we can call the helper function. And if the helper function returns true, we know that we have found our word inside the grid. Otherwise, if we have traversed all the letters inside the grid and we have checked for each of them, but if they form our word by selecting them as our first position, and we didn't find the corresponding word, we will just return false. Our helper function takes basically the whole board and our positions X and Y. This is basically our starting position, the first cell that we are using, and checking if it matches to our first letter in the word. Index is basically used to see where exactly what letter in the word are we currently checking in. So maybe we found the three letters that are matching the first three letters inside the word string that we are passing as the lace parameter. So in the next helper recursive call, we will increment our index so we can check for the fourth letter inside the word string. Now, the base case is basically that our index is equal to the word length. So that means that we have found the word and we return true. We have matched all the letters inside the word. The other case is that we are out of boundary. So we are basically either out of boundary by considering the rows, or we are out of boundaries by considering the columns, or the current character at the position that we are here in the recursive call of the helper function doesn't match the current letter that we are searching for inside the word marked by our current index. So we just return false. Next, we basically know that these two if statements are not right. So we know that we still have to find additional letters. We haven't fulfilled the first if statement, and we also know that the current letter matches some position inside our word letter. It can be the fourth letter that we have found, fifth letter, or so on. So we have to mark it in some way by a special character so that we don't get to this cell again by calling the helper function recursively. And because we know if we are only using upper and lower case English letters, we can just mark it by any other special character. Once we have marked it, we will check if we can form the word by using this candidate as the letter that matches the current letter marked by the index inside the word by calling our helper function recursively. And we have 4 directions to go. So basically, we'll go up, down, right, and left by calling the helper function 4 times and playing with the x and y coordinates. Each time we are incrementing the index, so we are searching for the next letter in the word. If any of these condition is true, so we have found the word letter deep down in the recursion tree by choosing one of these directions, we know that basically we can propagate the bubble up the result to the main function, so we can return true. But before we do return true, we have to backtrack. We have to make the letter basically change from the special character to the letter that we have found. And to do that, we can just use the word and the corresponding index to reset the value in the grid. And basically, we just return the exist variable, which represents if any of the direction worked for us. So now for the time complexity, we at the worst case, we are traversing through the whole matrix, and let's say the whole matrix contains only one kind of letter. The one letter is, for example, A, which matches the first first letter in our word. So we will have m times n calls of the helper function. Now, for the helper function, at the worst case, we can have the recursion tree that's deep L, where L is basically the length of the word. We don't go any further than the length of the word. We are using our first if statement to make sure that we are not going beyond the length of the word. And at each position at each cell we can have 4 options. So that's our width. So basically that leads us to 4 to the L time complexity times the maximum number of calls inside the for each cell inside the matrix, which is m times n. Now, in comparison to the previous problems that we had inside for the backtracking category, we don't have any copying of a list, nothing, but still we have the space complexity, which is equal to the length of the word. Why do we have that? It's because of the recursion stack. We have to keep track of the recursion stack each time, and the maximum size of that stack will be L, because we can have at most L recursive call stacked one on top of each other before we backtrack and roll basically bubbled up and go up in the recursion tree. So the space complexity is again L, which corresponds to the length of the word.